the graduates that are decided to attend this seminar, and colleagues and friends connected from remote. It's a pleasure to me to come back to this university. I have been involved in many engagements in the university since the 80s. And today we'll try just to provide some information about the essence of process safety. The aim is just to provide people, especially graduates and some colleagues, junior colleagues, with basic information about the profitability to understand what could be just a kind of destination of the let's say, the pathway and the road regarding process safety in the world. I apologize for being very fast in my discussion, because it is very difficult to try to, let's say, provide an outline of the basic nature of the process safety. And so it's very difficult to stop and just to tune exactly the cursor, stopping just in order to comply with the timetable. So please apologize for being very fast. Sorry, okay. Okay, this is, I think Italian students and graduates should know very well this picture. It is essentially the planned wedding or promessi sposi by the writer Alessandro Manzoni. Carnea de chi era costui. This is a Greek philosopher, and it is just a way to try to present, to introduce myself. The aim of my introduction is not just to provide any kind of publicity, but just to connect exactly my background, my professional and academic background, to the information that I will provide today. Okay, I will be very fast. I'm a chemical engineer. I have just been involved in any way academic engagements over the time. The reason was essentially just to notice that in order to be a professional engineer, you must be involved in your career, both into the professional, but also in the academic and scientific world. This is not just a way to probably comply with a personal approach, because probably the world is demanding this from young people. This is different from what happened when I was a child, because the world was much different than now. This is essentially my department in Brussels, in Belgium. I have just an involvement in the part of the physical chemistry department dealing with process safety, that is becoming a more and more important part of the chemical engineering. With the Mary Kay O'Connor Process Safety Center in Texas A&M, I had the pleasure to work with Sam Manan. Sam Manan is passed away a couple of years ago, but was probably just a pioneer of this is a very important department. Maybe it is now the most important department for process safety. We are dealing with 100 people working just on process safety. And I had the pleasure just to interact with them, working on reactive hazard assessment. I have been, and I am currently just a tutor, some university in the world, for people, for graduates or postgraduates who decided to follow up on their career regarding process safety. Unlike it happens in Italy, but I really look forward to seeing exactly this outcome to become real in Italy as well. In the United Kingdom, where I live, process safety has become a standalone discipline of a chemical engineer. This is due to two main reasons. First of all, the complexity and the specificity of the subject is such that it is now probably useless to probably cover process safety subject as a part of, let's say, the ordinary courses in chemical engineering. So it's difficult to have a completion of the coverage if you don't focus exactly on process safety as a standalone subject. This is the first reason. The second one, I think for chemical engineers, is now worldwide the most important, the most requested career that a chemical engineer can probably expect to achieve in their career. So this is very important. As you see, a couple of dissertation, master dissertation that I tutored in the UK. I also worked as a co-worker in Malaysia. This is essentially a seminar that I delivered in Malaysia, 200 kilometers far from Kuala Lumpur. This is Petronas. Petronas is one of the most important oil and gas companies in the world. They are implementing carbon capture and storage. It means separation of CO2 from the ongoing processes. This is implying some specific issues regarding the risk. It's difficult now today just to explain why, but CO2 is now an hazardous, much more hazardous than the past, because we are now dealing with much higher concentration. Those concentration ranges were not experienced in the past because, of course, carbon dioxide was not separated from the mainstream of a process industry. That's the reason why now we are coping with some additional issues with CO2. And so now I've been working, and I am formally still a co-worker in this university. This university is funded by the industry. You know that now the impulse in Asia, in the Middle East and Far East is very, very, very strong. So now we have a very important driving force regarding the relationship between university and industry. We have an engineering company located in the UK. This is the geography where we delivered our jobs. So maybe also Australia something, but mainly Asia, Middle East, Far East, Europe, and something in the Northern America. This is my very latest job in Middle East. It was a clean fuel project in Kuwait, $12 billion, 55,000 people every day commuting on the construction site. So every day, 55,000 people moved from home to the site to essentially implement a process where sulfur and nitrogen were removed just in order to achieve the final target consisting of clean fuel. So removing organic sulfur and nitrogen. So I was involved for 7 years working on unbelievable, very, very big issues regarding safety. Okay, my details, I will move very, very fast now. So the agenda is rise of the contest and incident scenario, just in order for you to be able to understand exactly what we are dealing with when we say incident, process safety, what is practically the final result, the final outcome in the market, in the world, in the industry, on site. Then we will move to what is process safety. We would try just to define, because sometimes wording is important, but we can have some issues in defining exactly what we are doing for. We'll try just to find a definition. Some principles and fundamentals. So you are now in university, and we are very lucky. You are very lucky because you are following a very important courses, and I know that Professor Sesti is implementing just a kind of a mixed information between academic and also, let's say, a site or a look to the industry. So principle and fundamental, some applications, practical application that we'll try to show and to demonstrate to you, hopefully in the next minutes. Rise of a contest and incident scenario. 5 incidents. I will try to be very, very fast. What is the context? We know that until the Second World War, in reality, the industry was, the chemistry, industrial chemistry was the chemical industry and the industrial chemistry consistent essentially of inorganic chemistry, ammonia, nitrate, chlorine, sulfur, glycerin. You remember, of course, maybe a relationship between these substances and the incident. You can see there is no organic, appreciable organic compound, just inorganic. We can see the relationship between geography, substances, event, and the final fatalities, lethality, and let's say the danger in general. In the 1950, 1970, so after the Second World War, nuclear industry developed novel concepts. So there was a scientific pushing effect regarding the necessity to find an inherently safe reactor. So the reactor must be inherently safe. We will try to understand what we're meaning with this, but process reliability, risk assessment, and inherently safe reactor come from the nuclear, and essentially from the early stage of the nuclear in the 50s and in the 60s. After that, we can see that due to the implementation, the discovery of the potential of the carbon atom, oil and gas and petrochemical industry, in addition to changing our life, when we were young, of course, because when you were born, you already found essentially the world completely, Mrs. Greta Thunberg would say, contaminated by plastic, but everything has been very much easier, also thanks to the organic chemistry, of course. So what was the change regarding our scope? Inventory, amount of substances stored on site, pressure, temperature, reactivity, thermal potential. They became huge, impressive, with no kind of connection regarding the past of the industry. The nature of carbon chemistry, with its huge binding capacity, we have a Lego system. You know the Lego system, the Playmobil, multiply the production pathways and the multifaceted chemical frameworks. So chemical people, they discovered the potential of an atom with the oxidation number 4, so with the potential to bind with hydrogen and heteroatoms as well. So toxicity became a relatively unknown challenge. There was no specific, in addition to Giovanni Verga, Rosso Malpelo, the sulfur in the mining, but there was no memory in terms of scientific and standard, in terms of what was essentially toxicity. Side reactions become a relatively novel scenario of the newborn process safety. Dow Chemical had big problems. Side reactions is a very important concept. When you say chemical reaction into production, we think and we believe that just the reaction we are looking at is the only one reaction that probably happens. This is not true. We have a main reaction. The reaction we are interested about is just the main reactions, but we have side reactions. And when chemistry became very complex, side reactions became very important and potentially hazardous and dangerous. Okay, incident that made an era, an incident that milestone the technology. I will try to run, please. Flixborough, UK, 1974. The process was related to the production of cyclohexanone, that is a ketone, from cyclohexane to provide the raw material, the feed for the production of a caprolactam. Nylon was not, at that time, was a very, very new material. So this was essentially the process. The process pressure was 10 atmosphere, and we probably ranged the process temperature between 150 and 200 degrees Celsius. Okay, this was essentially the process. Try to. No. It's not going on. Maybe. Okay. Okay, we are in the United Kingdom, Flixborough, 1st June 1964. The boundary conditions for the incident were, it was Saturday. This is very important detail. No senior management present on site, just junior engineer, 1-2 years of experience, shortage of nitrogen. Murphy law, do you know Murphy law? Yes. If everything hazardous will happen, it will happen with the worst condition around. This was essentially the situation. The process consisted of 6 boilers, tanks, where by gravity, the liquid reactive stream were conveyed from the top to the lower level. You can see from left hand side to right hand side. This is essentially the plant before the incident. What happened? A junior engineer, the 1st of June, found out essentially that the reactor number 5, between 4 and 6, was affected by corrosion. There was a crack in the shell. So decided to stop the plant, depressurize the plant to remove the boiler. And in order to start again, he decided to connect reactor number 4 and reactor number 6 with the dot leg, with the pipe. It was essentially a 200 millimeter pipe, as you can see. and this was essentially what was built on site. You can see here a photograph, a picture of the connection between the two reactors. The 20-inch pipe scaffolding was located on a scaffolding, on a structure, because it was very easy, very smart. And this is a situation that you can find in my book. In my book, I tried, because I am all the time university, so we studied also construction science. I tried to understand what happened from the point of view of the stress analysis. So I carried out a stress analysis calculation in order to understand from the structural point of view what was essentially the outcome and why possibly the plant collapsed. What happened in reality was essentially, you can see, the junior engineer started the plant again, pressurized again the plant. Of course, started from, let's say, pressure zero, relative pressure zero, to 10 bar, 15 bar. In reality, what happened, the two remaining reactors, number 4 and number 6, of course, they were pressurized, so there was essentially two forces, FH, that were depending on the pressure, that tried essentially to push the two reactors to each other. So there was essentially a kind of pushing effect that affected the pipe, of course. Of course, the structural system was affected by two horizontal forces, FH, that in turn resulted in a force momentum. The momentum was due essentially to the existence of a couple, force couple, FH, and the eccentricity, the distance E, that of course resulted in an overturning moment. The moment tried to overturn the system. There was a reaction momentum. The system tried to remain compensated, and to compensate the momentum, the system reacted with the two additional new forces, the vertical forces, the forces FV. The forces FV were vertical, and you know the second fundamental equation of static requires that the sum of the momentum must be zero in order to keep let's say, equilibrated the system. So the final result was the rise of a second momentum that can be calculated easily by essentially the multiplication of Fv by L. That was essentially the momentum that the system tried to locate into the plant arrangement to compensate the pressure. The bellows, as you can see here, we have the bellows, so the system. The bellows, this was essential for thermal relaxation and dilatation in order to compensate for the dilatation during the pressurization. But they were not designed to withstand the forces. So they were essentially, there was a shear stress that ruptured this. Probably cyclohexane came from here. So there was a rupture of the bellows, of the, let's say, the thermal stress compensator, mechanical compensator that were not designed, were not able to withstand the pressure and the shear, the vertical shear stress. So what happened in reality was, what you can see, probably the Court of Inquiry that worked on this incident for many years established that probably there was a flammable cloud that traveled from red, the plant, to the green place. The green place is the old hydrogen plant prior to the new implementation of the new technology consisting of the 6 reactors, around 100 meters. Probably there was the ignition point, so there was a flammable cloud that traveled 400 meters, reached essentially the old hydrogen plant. There was an ignition there. There was a witness that he reported that he saw essentially the flame from traveling from the green to the red. When the flame reached the red, there was an explosion. And the blue circle is the place where the control room were located. All people died. All people working at that moment in the control room, they died. So this is essentially the outline of the flammable cloud that was essentially, let's say, was rebuilt by the Court of Inquiry that was essentially involved in the investigation because this incident was terrible. We can see here what happened after the explosion. This is essentially what remained after the explosion. We can see just a kind of, let's say, the outline of the red line is where the dock leg was before. Human lives cost. 72 individuals present inside the plant. 28 were killed, including all people working in the control room. 36 were injured. Outside the facility, outside the plant, over the fence, 53 were injured. People that were not, they had nothing to do with the plant. They were just driving or working or outside. They were injured. Hundreds of other people sustained more mild injuries. The property damage, you can see what is the potential danger, why now our job, our work has become so important in the international project. All buildings lying within a radius of 600 meters around the explosion, destroyed, all the buildings, regardless of whether or not the building were inside or outside. 800 housing units damaged, 800. People in Flixborough, they were convinced that there was a war. They were bombing because 74 were just around 30 years from the end of the Second World War. They say they are bombing again. I don't know. People are coming with aircraft, and because it was a warlike explosion. It was a warlike explosion. 73 in Ascot, 73 in the town, in the village, in the nearby village where they were injured. 644 in Burton, serious consequences. Large piece of equipment found at 6 kilometers from the plant. You can imagine, 6 kilometers. Smaller debris found at 32 kilometers away. The fragments, the debris, are at 32 kilometers. You can imagine what was. 100 million, 1964 USD dollars. What is lesson learned? Control room blast resistant in the UK, outside processes in the UK were no longer allowed to be built in the process area. It was a national anticipated law in the UK in 1964. Inventory means if you have a kind of specific amount of substances, you must carry out risk assessment. It was completely novel, never carried out before. Spacing and layout in terms of the identification of appropriate distance between items in the plant became a reason of concern in the design. ALARP, that is a very important internationally, let's say, recognized word for identified risk. The ALARP method was implemented in the UK, and now it is implemented everywhere in the world, including Italy. The COMA is the control of major hazard, was a general procedure, and chemical engineering started to work about this kind of subject. Seveso, or Seveso in Italian, Seveso in English, Italy, 1964. I remember I was a child. What happened? There was essentially this Icmesa. We are close to Milan in Lombardy, and this apparently very simple process consisted of essentially production of trichlorophenol for let's say fertilizers, because we are in the 60s, so Italy was started in industrial development. What happened is essentially the rupture disk that was there for protecting the plant from overpressure collapsed, ruptured, and due to the fact that the stirrer, the mixer, was turned off, preventing the reaction heat to be well distributed, but there was an accumulation, because you know, in a reactor, when you have an exothermic reaction, if you don't keep on the stirrer, you can have what is called in English hotspot. Hotspot means that you have an accumulation of heat and high temperature that possibly can be not supported by the system. No cooling water added as well. This was the main factor. It was, once again, Saturday night fever. You know, Saturdays, you go in, I live in the UK, but my childhood in Salerno, when I come to Salerno in Saturday, say, oh my God, okay, but this is, I'm very old. Okay, this is essentially the concentration of TCDD, dioxins, because the problem was that dioxins, TCDD, trichlorobenzyl dioxins were formed. As you know, this is a carcinogenic compound. There is no more concentration is tolerated in the process, in the incineration, waste management, waste treatment, but there was no memory. We probably know that this is essentially, you can see, the toxic cloud, Flixborough was a flammable, here was toxic cloud, was as large as you can see on the map. Municipality of Desio, Cesano Maderno and Seveso. You can imagine. What happened, I remember, was a child and we only have 2 TV channels, white and black. And my mom called me, say, come and see what happened on the children face. This is for dioxin. This was not true. But what happened from overseas, from New York, from Los Angeles, from everywhere in the world, people, they were shocked because they saw that the children presented what you can see in terms of the skin affected by dioxin. It was not dioxin, but people didn't know. This is sodic phenate. This was essentially the sodium hydroxide effect, but people didn't know. So the impression was huge. Now you are in the social, Facebook, Instagram, and other channels available. So everything is now also a very minor things, immediately shared by everyone. So this is the reason why probably society is experiencing some problem in energy. This is my opinion, of course, because if you say a novel, and the novel can become a principle of physics, of science. Okay, at that time it was not that way. Communication was not in place, but this was probably the most shaded, worldwide shaded information. A New Yorker say, oh my God, the children from London, from Paris, from everywhere. So these people probably did not die. There were some problem with my pointer. And I don't know, Libero, I'm sorry. So, I don't know. Probably I should, there is probably a standby, I don't know, issue maybe. I must run. Okay. Yes, as you can see, the consequences, maybe 3-4 kilograms of TCDD were emitted. 3-4 kilograms is huge. It's a chemical war. Now we are dealing with ppb, part per billion. They were kilograms, unbelievable. 42 children out of 200 living in zone A showed chloroquine. It was just chloroquine, but people say the dioxins. They are dying. No. Possible cancer increased rate. So not immediate problem, but let's say long term, probably many people died for cancer. For, let's say, long term effect. Some genetic anomalies. The 7, I will be very, very, very fast. The Council Directive 82, I remember because this was actuated in Italy in 1988 with the DPR 175 was implemented in Italy. So this was essentially the certificate of birth of the risk assessment. The risk assessment, 74 in the UK only, and 82, 76, there was Seveso, 1982, and in Italy, 1988, was implemented in Europe. Phase-in, very important. This is an LPG tank farm. LPG is propane and butane. This is stored under pressure at atmospheric pressure. So we are around 10 bar and 20 degrees C. You can see here the propane vapor pressure. You can see that the normal boiling point is around minus 42 degrees. Whereas if we store under pressure, for essentially comply with the vapor pressure rule, we have essentially kind of around maybe 7-8 bar. So we had essentially, when you see the sphere, no? The round tanks and the propane, or also in your garden, you can have the LPG, the GPL, LPG. Okay, this is essentially what happened. This is the, let's say the storage condition is this. We are around 20 degrees, like now, maybe something more, and the corresponding vapor pressure. So we are keeping liquid, the LPG, by pressurization. What happened? In reality, if there is a leakage, if we have a release, there is suddenly the system realizes they are at different pressure. The system must react, just boiling off the liquid, because the system will realize that at atmospheric pressure, the vapor pressure must in reality reach minus 42 degrees, because this is the normal boiling point. So the boiling point at atmospheric pressure. There is no way to receive heat from it just in order for the latent heat of vaporization. That's the reason why you can see that there is some liquid that provide the latent heat requested for the vaporization. So you have essentially what is called a flash. Flash means the liquid goes from 20 degrees to minus 42 degrees, and you have a fraction of liquid and a fraction of vapor, not gas, but vapor. because different between vapor and gas. So this is essentially just a simplified equation that normally is used in risk assessment when you have to comply with the leakage from GPF or LPG. What is the, let's say, the incidental scenario? UVC, unconfined, vapor, cloud explosion, flash fire, pool fire, and possible blame. What happened in reality in France? We are in the 60s. This was, as you can see there is the Elf refinery, and you can see what happened. What happened? There was an operator that was essentially operating a valve, drainage valve, in order to essentially remove water. Because you normally have essentially some water in all the, and hydrates essentially, in the storage of this kind of liquid. This stupid and poor operator, he opened the drainage valve, the bottom of the sphere, of the tank, and he realized that in reality there was essentially the cooling effect. So the temperature dropped down around the -40. He was essentially completely freezed, you can imagine, and he tried to close again the valve, but it was impossible. Because the temperature was embrittlement, a lot of problems, he was not able anymore to close the valve. So there was essentially you can see what happened because the flammable cloud, the LPG, left the tank, moved, there was a flammable cloud, it was essentially overnight or early morning. The flammable cloud reached the highway. There was a poor driver that he was responsible for the ignition. He ignited the flame, the cloud. So there was essentially, once again, a flame. The flame traveled to the tank, and there was essentially a blaving. Blaving is an acronym that stands for boiling liquid expansion vapor explosion. So you reach essentially, you leave the elastic property of the steel, you enter into the elastic, and you have a creep, and you can have just a rupture. What can happen is a pool fire. Pool fire means you have a pool that is the accumulation of liquid due to the collapse. Of course, the worker died, and it was carbonized. It was no longer recognizable. It was a piece of carbon. I've seen the pictures. This is not the only one incident that I have just seen personally. There was essentially just escalation. So the pool fire resulted in affecting all the other tanks. And so you have a blavy with a fireball, 100, 200 meters high. You can imagine what happened in Fezzi. You can see here, this incident and the blavy. This is essentially the chapter number 17 of my book, where I have tried to provide a thermal balance that works very well now, considering that, of course, radiation rather than conduction is the governing heat mechanism transfer. And you can see there, you can see the Stefan-Boltzmann equation inside and outside. And I can find exactly what happened according to the American standard, that the API 521, that is a governing standard for this. So boiling liquid expansion vapor explosion, you can see here what this is a fireball, you can imagine. Sometimes, normally, firefighters die when they are cold because the burning duration is very long. And when firefighters come inside, due to the radiation that is unbelievable, many of them normally die, unfortunately. Here, that's the reason why, now recently, I know that Professor Sesti has provided you with the basic elements of the PNID. You can see here some mysterious code, CSO-CSC. It means car seal open, car seal closed. The worker had not been able to operate a hazardous valve. That's the reason why, when we carry out a HAZOP, we normally say, during the HAZOP brainstorming, can this valve, make this valve left free to be operated by anyone? And if not, car seal open. This is a pressure relief valve. This valve, the intervention of this valve is when you have an overpressure that can rupture the system. So there is a set pressure, and so there is a pressure relief that can protect the system from the rupture. And now, if there is a valve that can be inadvertently operated, you can find on the PNID CSO. It means car seal open. So there is no ender. So no one can easily operate the valve. Because if you close this and you have overpressure, the system will collapse. This is a lesson from physics. Paper alpha was terrible. I will be very fast. Essentially, just a pressure valve was replaced with a flange. The flange was just sent off, and it happened what you see there. 5 out of 226 operators died. Many of them, they tried to save themselves just diving into the sea, but they were essentially just burning. You can imagine what was on a platform. Platform is a very congested and small place. 1.5 million US dollars. This is probably an injury, a wound in the West ethic system, because there was essentially a Union Carbide plant MIC, methyl isocyanate, was produced and used for additional reactions. What you can see here is a scrubber. The scrubber was a protection system for any release of MIC. MIC is very poisonous, very hazardous. What happened, the plant was stopped. There were 2 isolation valves in addition to prevent from any escape of MIC. There were 2 additional barriers. The plant was stopped, but both the barriers and the valves didn't work. They leaked. The MIC arrived to the scrubber. There was no water. There was very simple system. The system was essentially just relying on feeding liquid, and just in order to capture the MIC and preventing from escape from the stack, but there was no water overnight. This is the methyl isocyanate molecule, as you can see. The IDLH is 20 ppm. IDLH is immediately dangerous to life and death. It's essentially an American terminology dealing with you have 15 minutes to leave on your legs, the site on your legs. It's very low. There was essentially a huge amount of MIC that left. What happened is unbelievable. The root and immediate cause was isolation valve tightness failed, additional barriers broke down, water flowed into the 40 MIC, the scrubber didn't work, flare didn't work. Nothing worked. You can see what happened. It's unbelievable. I don't know how is it possible to be, I don't know, around 20, immediately around 2,000, more than 2,000 people killed. They didn't wake up in the morning anymore. They died while sleeping. We are in India here. We're in India. 20,000 short long-term killed people. So the several investigations showed that probably many people were affected by long-term risk, and they died after 6 months because MIC has different toxic and hazard profile. Affected people was 500,000, just for a very simple system with the water that should, you can imagine what. Okay, this is essentially the scenario of Bhopal. Imperial Sugar, I don't know the time, but I would like to, if we can just, because we have a video, because you know, in Italy we say dove c'è barilla c'è casa. Sugar, flour, coconut is dust, but you remember we worked together 30 years ago with Giorgio Donzi, and we were very young, many kilograms ago, I remember. And you remember, you know, flour and sugar, they can explode. There is a video, I don't know if it's the case to and then to pass to the second module. And if we can just, I'll try to accelerate the video, but I want to show you what happens if you when you have, just the folder where we have located the files, you can, sorry. No, there is in the folder, you have the video. Okay. I can show you, this is essentially an incident, Imperial Sugar Company. When you say the sugar can explode, people say, you are crazy, sugar is Ferrero, is just Nestlé, is Baci Perugina, but in reality, I will try to accelerate if I can. What happened? We can stop a certain moment if we are going. This is Imperial Sugar Company. At 7:15 p.m.
on February 7th, 2008, a series of violent sugar dust explosions devastated the Imperial Sugar Refinery in Port Wentworth, Georgia, just outside Savannah. Explosions raced through the buildings, fueled by accumulations of combustible sugar dust and sugar that had spilled from equipment. Thick concrete floors heaved up, and brick walls were blown into stairwells and work areas, blocking many exit routes. Fires spread rapidly. 8 workers died at the scene. 6 more died later at a regional burn center. Dozens of others were injured. The plant's massive sugar packing buildings were a total loss.
The accident at Imperial Sugar was the deadliest industrial dust explosion in the United States in decades. It highlights the extremely serious nature of combustible dust hazards.
There were significant accumulations of sugar dust and spilled granulated sugar on surfaces throughout this facility. Conditions were set for a catastrophic accident.
Imperial Sugar's sprawling Port Wentworth complex began operations in 1917 and grew to become one of the largest sugar refining and packaging facilities in the U.S. Granulated sugar from the refinery was stored in 3 100-foot-tall silos and then conveyed into packing buildings where it was packaged for distribution. Granulated sugar was also converted into specialty products, such as brown sugar and powdered sugar. Sugar was transported by a complex system of bucket elevators, screw conveyors, and conveyor belts. During this process, sugar spilled onto floors throughout the work area. In places, the spilled sugar was many inches deep. This sugar also contained fine particles, which became airborne. In addition, hammer mills were used to crush the granulated sugar into powdered sugar, creating even more dust. The machines were connected to a dust collection system, but it was undersized and in disrepair. And it was not connected to the bucket elevators and conveyors. Significant amounts of sugar dust escaped into the work areas. Workers routinely used compressed air to clean packaging machines, further dispersing sugar dust throughout the buildings. Over time, large amounts of dust accumulated on elevated, hard-to-clean surfaces, such as ducts, beams, and light fixtures. These surfaces were not cleaned often enough to always keep the dust below hazardous levels. In the tunnel beneath the sugar silos, granulated sugar flowed through chutes onto a long steel conveyor belt. From time to time, clumps of sugar would become stuck in one of the chutes, blocking the flow of sugar on the belt, spilling sugar onto the floor and releasing dust into the tunnel. But the tunnel was large and ventilated, so this airborne dust did not build up to explosive concentrations. However, in 2007, the company enclosed the conveyor belt with stainless steel panels to protect the sugar from possible contamination. The enclosure was not equipped with a dust collection system. As a consequence, sugar dust would now be trapped inside this enclosure. On February 7, 2008, clumps of sugar were found blocking one of the discharge chutes. Sugar from the adjacent silo likely spilled off the moving belt. Dust likely accumulated to an explosive concentration inside the enclosure. At about 7:15 p.m., the sugar dust contacted a nearby ignition source, likely an overheated bearing, and exploded. This primary explosion blew apart the enclosure and vented into the packing building. Accumulated sugar was lofted and ignited by the advancing fireballs. The dust clouds fueled a chain reaction of secondary explosion, which swept through the building. Concrete floors buckled, releasing tons of granulated and powdered sugar into the flames. Emergency evacuation drills had not been conducted, and the explosions had cut the power to much of the interior lighting. In the maze of darkened and damaged stairwells and passageways, workers desperately tried to flee the growing inferno.
So you see, So all organic dust can result in this explosion for lack of housekeeping, maintenance, housekeeping, and design as well. So United States, the second one, thank you. So this is essentially the scenario where we are moving just to present now some principles and fundamentals. So you can see how important, we have a lot of incidents, these are the most important, but we have much more than this. What is process safety? We have referred main definitions and the calculation formula to my book. The book has been generated after a specific course that I have delivered in the UK. And after that, I was asked just to maybe organize something like a book. So this is the reason why I'm just, the book is here just for you to have a chance to have a look. What is process safety? The key definition are hazard, risk, severity, and likelihood. Hazard is a potential for harm. In Italian, it's pericolo. There is a difference between pericolo or hazard and risk. Pericolo is an inherent property of the substance, of the context. There is nothing to do about to eliminate the inherent property. If you have a property, you have the property. So this is hazard. Hazard is an intrinsic property, a potential for harm of a substance, process, context, which does not depend on modalities and so on. It remains in place. For example, when I was young, hydrazine was used to remove oxygen, was an oxygen scavenger to remove oxygen from boiled water. As you know, oxygen is potentially responsible for corrosion in boiled water. We used hydrazine, that is N2H4. The reaction with oxygen was just molecular nitrogen and water. So it was perfect, but in reality it is carcinogenic. So it was essentially an hazard. What happened is what you can see. This is CLP. CLP is the classification, labeling, and packaging European regulation. It's a big book that can provide you with all information that you about substances. You have a CAS number, you have the substances, and you essentially you have the risk, toxicity, noxious, and so on. So you can see how hydrazine is hazardous. For example, you can have essentially hazard detonation versus deflagration. As you know, deflagration is the travel of a flame at a velocity that is lower than the sound speed. This is deflagration. When you have a candle, this is the deflagration. Detonation is what happens when the flame speed essentially just exceeds the speed velocity. As we can see, depending on the reactivity, hydrogen and acetylene, they high reactivity. This is so more hazardous than methane. The laminar burning velocity of methane is 40 centimeters per second. The laminar burning velocity of hydrogen is around 380. So it means that when hydrogen will be implemented in the ecology transition, is a fantastic name for the new minister. I'm not understood what does it mean, transition ecology, but it's fantastic. Consider that you are going from low reactivity gas, fuel gas, LNG, to high reactivity. It means that the design, the handle, the management of hydrogen is potentially inherently much more hazardous than methane. This is hazard. Risk is a combination of likelihood, that means probability, and severity of an event producing death or serious injury. In the risk assessment study in the industry, there are toxicity, thermal radiation, and overpressure. When some of you who will become sooner or later, because you will be a process engineer, 95%, especially because you are more guys. Sorry guys, but we are winners. So you are normally smarter than us. You are smarter than us. So process engineer is a very good job for chemical engineers. After 2-3 years, you probably say, but now I can see what happened in health and safety and process safety. So this is essentially the three main bands of risk: toxicity, thermal radiation, overpressure. Risk is normally expressed as a frequency. So it's a number of incidents over the time. You can see here essentially, it's a very important risk matrix that is used in the industry. When I started working on this, it was just people. Just people. After 5-10 years, environment. Now, when we carry out studies, there is asset, reputation, business interruption, property damage. So we the process safety engineer will be involved in ensuring that not just people or environment will be potentially affected and must be protected, but a lot of this. So the process safety engineer is becoming one of the most important actors in the chemical engineering studies. Okay, severity. What does it mean, severity? So severity means quantification of consequences. Here we have the American Conference of Governmental Industrial Hygienists that provide you with some specific. So when the Seveso incident happened, or Flixborough, there was no memory about this. I remember, I was a child, I remember that I saw on the TV that some Americans came from overseas because they were much more experienced about toxicity. In Italy, we didn't know anything about toxicity, about dioxins. So there was a big confusion. Now we have this. TWA tell this is probably the most important international standard and association. It's highly reputable. In Italy, this is recognized if you have some problems, or if you apply rules about process safety. This is one of the main references. TWA means time-weighted average. It means that essentially is a concentration that you can tolerate over 8 hours working day. STAIR is an acronym, meaning short-term explosive limit is around 15 minutes. You have a molecular weight, and you can have some information, ammonia, ammonium chloride, and so on. This is essentially a very important slide because we can collect information about some important codes regarding toxicity. This is released by the NIOSH. NIOSH is a National Institute of Occupational Safety and Health, the American Association. You can find the NIOSH spoken guide you can download from the internet. You can see the IDLH, immediately dangerous to life and death, for hydrogen cyanide is 50 ppm. You can see what is the STAIR, the WA, you can see some chemical and physical properties, and so on. So you can capture a lot of information that can support you in the development of process safety study. For example, H2S, you know H2S is just a smell of rotten egg, is when something is going wrong about food, you normally can perceive why. Our nose is designed to capture when proteins break down. That's the reason why our odor sensitivity is much more related. We can probably perceive that something is going wrong about food, fish, and any other food, because below 1 ppm of H2S or ammonia, because nitrogen and sulfur are probably let's say, the leads of some specific mercaptans, amine, and so on. That's the reason why our sensitivity is so strong. But after 200 ppm, it is no longer perceivable. You cannot feel the smell. That's the reason why some people, when they try to enter the bank, sometimes they are found dead. And normally they have the mouse, the rat, because the rat, if the rat dies, it means that you have a high concentration of H2S that is impossible for your nose to perceive the odor. But you can see what happened. And in the industry, you have a lot of situations where you have this H2S and hydrogen sulfide compound. Thermal radiation is the second other. Normally you have jet fire, fresh fire, pool fire, fireball. They are expressed in heat flux, kilowatt or square meter. You can see here, we use this in the studies. Sometimes when you develop an emergency plan, you have to see what is the distance that you have to cover in order for your people to be safe. So you have to run away. If the road is very long, here you have the time that is essentially here. You can see that is required for your skin to perceive and to be, let's say, injured by heat. You can see here is the so-called pain threshold, the pain threshold. So after some seconds, as long as the time goes on, you can have just an increasing pain on your skin. This is very important because this is released by international standards. It isn't just academic. Comes from academic studies, of course, because science, technology, technique, and application. This is the science is on the top. But this is essentially IOGP. Is an international standard collecting together information from oil, gas, and chemical company. You can see here, we use this for the emergency plan. You can see then overpressure. Overpressure, two main problems in the process safety: buildings and people that are affected by overpressure. The lung, the chest is broken and you can die, depending on the overpressure. So you can see, for example, here, we use a picture like this to identify what happened when we have an explosion for people in the offices, in the control room. Possibly, if you can see, we have just a relationship between the probability of lethality, probability of death, and overpressure. The investigation carried out for Frictor demonstrated that the roof of the control room collapsed. All people died because it was too near. That's the reason why when you carry out an analysis on a plot plan or layout for a chemical plant, we have to argue about what happens, for example, for people living in a steel frame B2. We go into B2 line and we can correlate overpressure and lethality. And we can have an information that we include in the process safety report, informing about what is the likelihood, expectation about the probability of death for people affected by overpressure for people inside the building. This is additional health and safety, UK health and safety executive that is providing information since Flixborough. We have a lot of information about the probability of the consequence, probability of death for people against the overpressure. We can see 0, 0.2, 0.3, and so on. Here you have essentially what is the specific effect of the overpressure related to the injury, skin lacerated threshold, serious wound threshold, serious wound, and so on. You can use this for your risk assessment. It is one of the main tasks of a process safety engineer. This is the very important clumsy distribution. When you locate the building, or if you have a temporary building for construction site in the chemical industry, you have to ensure that in reality, let's say the effect of the overpressure is absorbed by the building. We can see here that we have a kind of list of damage depending on the overpressure. This is one of the most important classification relating damage against overpressure. Very important. So this is the third band. Quantification of likelihood. We can say that quantification of consequences, these are consequences. These are not affected by probability. And this task is completed by applying the engineering discipline. Thermodynamics, physical chemistry, fluid dynamics, structural engineer, and this is consequence assessment. But we know that we have, in reality, probability. The probability is important because I hope not to be a prophet, but if this roof drops down, this ceiling, probably we can die. So the consequence will be terrible, but the probability is very low. The risk is very low. Now we will discuss about likelihood, probability. We can see, normally we discuss about loss of containment. Risk assessment, unfortunately, is just loss of containment. We have a loss of containment, so we have a release of substance, toxic, flammable, and so on. So we have essentially, we can see there, momentum, buoyancy, and passive dispersion. We have a kind of a sequence of fluid dynamic regimes regarding the outcome of the release gas or vapor. Of course, momentum means that you have a very high Reynolds number. So velocity, the release velocity that normally is around 200, 300 meters per second is the speed velocity, is the governing parameter for that. Then depending on buoyancy, that means that if you have, for example, methane, you can have essentially the buoyancy is positive, you can have that the methane goes up. But if you have a very heavy substances, probably the gas goes down. So the buoyancy will affect essentially the second phase of the transition for a release gas. Then you have, in the end, regardless of the molecular weight, so heavy or light gas, you have a passive dispersion. The wind, gone with the wind. The wind will govern, will drive the final, let's say the final outcome of the release stream. You can see here, I think this is nice, because I'll try to summarize for you what is essentially the logical sequence when you carry out a risk assessment. You can see there is every kind of subject that you studied, because you have to appear everything. From chemistry, from physics, from maths, to physical chemistry, everything is here, everything. It's incredible the number of competencies that is required from people working in process safety. So we have essentially rupture probability, release, then we have a dispersion, and we can have an ignition. We can see, for example, that the release is, let's say, represented by consequence assessment techniques and the thermofluidynamics. Dispersion, again, and ignition probability. This is the sequence. Here we can see, for example, I will try to be, we have some release frequencies of some plant or equipment. Pipe, flange, manual valve, these are standard These are not just academic. This is originally academic. They come from statistical study, are used in process safety in order to size exactly, to have a kind of dimension of the release frequency when we have a plant. Reactor, pipe, filter, distillation column, everything you can imagine in the chemical industry. Actuated valve, motorized valve, no? And here you have essentially pressure vessel, frequency, you can see, you go and you capture, you collect an information regarding the frequency because you need the frequency, because risk is a combination of frequency and consequence. Centrifugal pump and so on. Unfortunately, we have to consider that going to the wind is important. So you can imagine we multiply all the frequencies, all sides, everything by the probability to have a specific wind speed in a specific direction. And we have to mathematically combine together all this information. It's huge. You cannot imagine. We have tens of thousands of information that we have to combine together in a process safety study in order to have something that is robust in terms of the theoretical. So this is the wind rose. For any location, we need the wind rose. Every 30 degrees, 15, 30 degrees, Nicola, more or less, we have to consider, recalculate again, with all the probability. In the end, the probability will be combined together, taking away all the information that we have collected from the beginning of the risk scenario. And in addition to the wind, we have the weather stability, because from A to G, we have a completely different behavior of the stream, of the toxic cloud, of a flammable cloud. Normally, this is a rule of two, we use D and F. Why? Because F is stable. It means that the stream, when you see in a very nice day, and you see an industry, and you have a stack, you can see that the stack emission is very stable. So it's not changing because depending on the stability. When it is very stable, what is F? F means that concentration are kept together, is very high, is not diluted with air. That's the reason you normally use F. You normally use D as a neutral because it is statistically, there is an experience about weather stability, Gifford, Pascal and Gifford category. They are used for the consequence assessment, probability assessment. D is statistically the most important. So we normally recalculate everything we say between D and F. We can see here the weather categories. Here we see this is wind direction distribution collected from our study. We can see a lot. We have a lot of information. You can imagine, and sometimes we use our software. You can imagine. You correlate 1,000 of information like this. Here you have essentially the quantification of ignition probability, because if you remember before, after the release, after the dispersion, after, in Fricksboro, the flammable cloud traveled and the ignition was at the hydrogen plant. So, in addition to everything we said before, we have to add ignition probability. That is not 1, can be 0.2, 0.3. We normally use calculation like this. I don't enter the details because there is no need. Risk is normally, remember, there are two kinds of risk. Catastrophic is immediate risk, and occupational. Occupational is, for example, for when you have you can have some specific chemicals that don't cause an immediate, when you have asbestos, amianto, asbestos, there are probably time in order for the let's say the illness to become evident also for 2 years. This is occupational. Occupational means, for example, that you are breathing something that you can have headache, you can have stomachache, you can have some problem regarding your well-being. It is occupational during the normal operation. This is important for process safety. But you have catastrophic. Catastrophic is easily understandable. We can see what does risk mean. For example, you know here what is the most hazardous or risky situation between acetylene and methane. I would say if I look at the ARM, safety data sheet and the properties, I would say the first one, because acetylene is much more, it's much more hazardous inherently. But if I have a welded pipe, probably the frequency to have a release of acetylene is very low. If I have methane, is less hazardous. But if I have a flanged connection, probably I have much more. It's much more probable that I can have a release. So it is much more risky, the second one. This is in order for you to understand what is the difference between risk and hazard. Okay, risk. You say risk, 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 but we have specific identification of risk. Typically, individual risk is, in the safety studies, individual risk, every person. We have a location-specific individual risk, we have individual risk per annum. In order to complete exactly a safety study, we must ensure that this specific, let's say, specific code must be within a specific range in order for the risk analysis and the plan to be acceptable. Otherwise, it cannot be operated. So, what is location-specific individual risk? It's the probability of a death of a person that will remain there in an X, Y, Z location for 24 hours a day, 365 days per year. Location-specific. So, it is not related to the probability of the person to be there, the worker, the engineer, but it is for all time. This is a location-specific individual risk. Then we have essentially, in reality, this should be, okay. Of course, we can have alkylation plant, we can have essentially oxidation plant, we can have sulfur recovery, so we have X, Y, and we can add together in order to have the overall LSIR. We can combine together, we can sum all the risks, depending on the combination of the risk. Normally, as I said before, risk means toxicity, thermal radiation, and overpressure. In the end, we can sum up all the LSIR to obtain the location-specific, overall location-specific individual risk. We can see here what is the final evidence of a risk assessment. People, the managers, the directors, engineers need, and also people involved in the design, must be able to manage a diagram like this. In this case, we have different frequencies, and is a frequency of death. So, of course, we have a kind of, let's say, you have several 10 to minus 3, the probability, the frequency of death is 1 is 1,000 year, 1 is 10,000 year, 100,000 year, 1 million. LSIR at constant frequency courses. In the end, an escamotage, in order to reduce the risk, sometimes we don't use this, but in reality, according to the UK, that is the worldwide applied, we use the IRPA. IRPA means that, okay, we have a location specific for 12 months, but if people are there only 6 months, 1 month, 15 days, is the risk the same? No, it is IRPA. The risk of death or serious injury to a person, considering the fraction of the year spent there, this is a, I don't agree with this, but it is a rule. Sometimes people increase the number of shifts, turning. So you have 3 shifts, 8 hours, 8 hours, 8 hours, you multiply the LSIR by 0.33. But if you go to 4 shifts, you multiply by 0.25, so you can reduce. In reality, the risk is always the same, but you can say, okay, but I have reduced the individual risk. This is very important, essentially, in the platform where you have people, because depending on the shift, for example, you can keep people 7 days in a platform, in an oil gas platform in the sea, free, and 7 days only. But you can say, okay, let's say 2 weeks free and 1 on, you can reduce the risk. In reality, there is always a person there. So if the incident happens, people will die. But in terms of the international, you can reduce the risk, and you can say, I reduce the IPA, not the LSIR. Okay, individual risk so can regard workers and society. We have seen Seveso, people were affected, the children. So we have workers that can be affected, but also the public, as the English say, the public. So you can see here, this is for you. You will remember about myself, not because I am special, but because this is very important, and I'm sure 30% of you will be affected. All of you will be affected in the future about this. 30% of you, sooner or later, will work as a process safety engineer, because chemical engineers, I'm very proud of it, we are probably the best engineering discipline for covering process safety. You remember the ALARP model. ALARP model was created in 1974 in the UK. The HSC, ALARP means as low as reasonably practicable, 1974, exactly the same year when Flixbor happened. What you can say about this? It's very important. It's the heart of the system. We have the risk, but risk is acceptable. Yes, no? It depends on the local sanitary controller. What does it mean I have a risk? How can be defendable to consider my risk acceptable? There must be some rule. The rule is the one provided by the UK Health and Safety Executive. Why? Because in the 1974, they carried out a very long statistical investigation. And so they say that we can be statistically defendable if we say that there is a broadly acceptable region. It means that if the risk is below once in 1 million year, 10 to minus 6, okay, I can relax. I can go to Positano because nothing to do. My job is finished. If I am higher than 1 in 1,000 year, no, the design must be revised. It is not acceptable. There is an intermediate band that is the ALARP band. What does it mean? Normally, you will see in next years that when you will attend design, and the process safety manager will say, what is the final outcome of the risk assessment? You will fall here. You will fall it's very unlikely that you can see here, because if you are here, it means that you are not making profit. You are a philanthropic person. It's impossible, almost impossible. Sometimes it happens that you are here. But if your design is correct, it's unlikely you are, because you are applying state-of-the-art technology. So it's unlikely both to fall in the broadly accepted region and in the red one. You fall in the ALARP. The ALARP means that you are not free. You cannot go to Amalfi, unfortunately, unless it is Agosto, because in August, in Agosto in Italy, you have to work further. In reality, the ALARP band for workers is between 10 to minus 3 and 10 to minus 6. For people, it's 10 to minus 4. There is a restriction. Why? Because if you are a worker, you have a training, you have been instructed, you have an education, you are an engineer. So you can probably accept to have an higher risk. But if you are a child, if you are an elderly person, if you are a housewife, you cannot, and you are in your house, you cannot. You are completely unaware about risk. That's the reason why the UK ALARP system identify exactly the unacceptable region in much more restriction for public. What does it mean? This is an addition, but I will try to, for never cards, it's a little bit tricky, but it's a way to cumulate together the incident to see where you are. There is again broadly acceptable, unacceptable, and ALARP. What does it mean, ALARP? ALARP is provision and maintenance of plant and system of work that are safe and without risk so far as reasonably practicable. It means that you are requested, if your risk falls within the ALARP band, to demonstrate that it is a sensitivity analysis job. If you try to reduce the risk, what is the cost? Because unfortunately, the problem of people that can die is an economical problem. It's an ethic problem, but when you are an engineer, you are dealing with $1 million, unfortunately. So it is economical. So if you demonstrate that, if you increase, if you reduce the risk further, you have a disproportionate cost, okay, it is acceptable. Otherwise, you have to implement an addition. This is a lot. This is essentially, this is an example. You can see offshore and onshore, the number of people on site. We said before that you can have a fraction of the time that you can spend on site in order to be eligible to reduce your risk. This is essentially what we said before. Okay, so after this, process engineer. What is process engineer? I think it's very important, in my experience, to differentiate process engineer from process safety engineer. This is my attempt. You can accept or not, it's my definition. Process engineering is the outcome of process engineering strictly comply with the design specifications, implemented through the simulator according to the license requirement. Any process deviation predicted, properly managed by the control system. Unit operations, distillation, absorption, and so on. It's unlikely that you can have a big departure of the behavior of the plant with respect to specification. This is process because you are designing. Unfortunately, process safety you don't know exactly what can happen. You don't know. You can have a prediction, but the allied uncertainty is absolutely huge. So the outcome of process safety present a much larger qualitative and quantitative uncertainty. The adoption of software simulators, predictive models is not as effective as for process engineering. Of course, because if your plant is okay, everything is going according to the design. If not, you can never know. So it's much more difficult. The bunch of competencies required from process safety engineering is highly multidisciplinary. It's unlikely that someone say, what is the stress of a flange? Yes, you can increase your background as long as you work, but when you say pressure vessel, you probably must understand something about structural engineer when you are process safety engineer, much more. The international regulation has introduced that they require new specific techniques. Huge. The reason why there are specific seminars in the UK, masters, and also faculty about, the reason is this, because it's completely. Okay, principle and fundamentals. This is the book. Okay, this is my master, this is Professor Gianni Assarita, was the chemical engineering for sure in Italy. He passed away in 1957. I have dedicated my first edition of the book to him. I miss him a lot. It was, I'm very proud to have had the chance to be his student in the 80s. This is important, it's very important. And I think it's very important, and I'm very happy that I have the chance to share this with Professor Sesti, because much more than in the past, the link between industry and university for process safety now, they are just one. And when I studied, the academic science was probably much ahead compared to the industry. So there was a gap. Now it is not forgiven. Sometimes industry is much more updated background than to the university. So they have to work together. It's you can see the standard is the standard regulation. Okay, my book, that's the reason why I have taken the book, includes some fundamentals. I don't know a book that specifically have included fundamentals for process safety, not fundamentals, fundamental related to process safety. So that's the reason why when I decided, why I was requested to write a book, as you can see, chemistry of process safety. Chemistry, but for process safety. So you can find here how important is specific information about chemistry regarding process safety. You have thermodynamics and thermokinetics for process safety. Second chapter, third, reaction engineering for process safety. Speed, you can have other books, but this is for process safety. There are some specific reaction routes that are specific for process safety, and if you know in advance, it's much better. Fluid dynamic for process safety. This is partially covered by chemical engineering. We studied the Navier-Stokes equation, where we studied hydraulics, because we are very old. So I'm very proud we were forced to study hydraulics, because in Naples, I graduated in Naples, and hydraulics was a mandatory subject, so we also carry out the information study about, but fluid dynamics is much wider. So this must be probably covered by process safety engineer much more than related to the information that he received during the graduation period. This is new. I found out when I started working in the 80s that I had to keep my structural engineering knowledge very fresh, because we are engineers. What differentiates us from Maria? Maria is an industrial chemist, as also my wife is an industrial chemist. Of course, I was a teacher, so I had just a dominant position. Then we married. Now she's the boss, of course. But what differentiates essentially a chemical engineer for industrial chemist is because we know structures, we know machines, they know process. They are very similar. But so this is important. Explosion, static pressure, dynamic pressure. You can see all information related to the overpressure explosion. It's very important. Consequence assessment. I will be very fast. We will focus exactly on the release analysis, event analysis, and consequence assessment. This is a complete flowchart for risk assessment. When we carry out a risk assessment, we will follow this flowchart from the identified streams through design data, chemistry, data sheet, technical specification, the process, description, everything is related to production. Then we have an hazard. We can see what is the hazard. Hazard, sensitivity analysis, significant scenario, probabilistic, and we arrive to the UK allowabilities, MSIR, and tolerable risk. This is now in every international and national project, energy, industrial chemistry, wastewater treatment plant, this is now mandatory. It must be covered. Modeling. We have seen that we have a release, we have a dispersion, and we can have an impact. This is the three main sequence. When you have a release, we have source models. So the source models are the models that help us discover what happens if we have a release of a liquid, of a gas. So source models, they are validated models. So we now discuss about this. This is essentially the sketch of the dispersion key drivers in the physical scenario. You can see. You have essentially the source models, just in order for you to understand how important is the knowledge of the source model that rely on the transport phenomena equation that you studied in chemical engineering principle. You can see this is essentially the table of contents of my book. Liquid, subcooled, boiling, transition, flash, rain out, droplet formation, snow out, sometimes you have solid, CO2, dry ice, you have solid, you have snow out. So it means that below 5 bars, CO2 cannot exist as a liquid. So if you go below the triple point of CO2, that now is the new challenge, because CO2 is, because we have a global warming, because Greta say, I will never fly again if I don't have an aircraft with hydrogen, because, okay, Greta, okay, good. No, because this is the power of the social, no? So you don't need a degree, you speak, you are very fluent English, you are a child, so you must be very, and every person that is governing a nation say, okay, Greta. But in terms of, I have a degree in engineering. No, it's Greta. Greta knows everything. Okay, anyway, so you can have a snow out. You can have a snow out if you have CO2, and you have essentially a release of CO2. You have an equilibrium, gas or vapor, and solid. So you can have a snow out. What happens? If you have a gas, the gas goes away. If you have a snow, you have the accumulation of solid, and you can be poisoned, and you can die for CO2. It's completely new, because you can have an accumulation, and you can have a sublimation of the CO2. And so when you carry out a risk, as it happened to me in 2011, when Greta was 3 years old, I was already studying engineering, I remember we covered the first design in the world for ENI in the Libya project for the removal of CO2 from a well gas. And so I started knowing and studying about CO2. So we also this. Then we have gases and vapor, so you can see how many source models we have. This is liquid, is the Sevin or Torricelli formula regarding the static head, and you can predict what is the release. This is essentially gas flow from pressurized containment. This is an adiabatic release, because the release is so fast that you can speculate and say that it is adiabatic. Normally, you can see the K, that is the let's say the CP and CV ratio. This is a two-phase flow or pressurized liquefied gas. You remember phase-in incident. This is what happened. Simplify the equation of a Cronin maneuver for fresh liquid. I said before, suddenly the liquid realized that it's no longer pressurized and is atmospheric pressure. So must be vaporized. Where is the heat for the vaporization? It's provided by a fraction of that become liquid. So you can see, and this is very important, because you have, in reality, some liquid. The liquid fraction must be dealt with according to the pool vaporization model. We have some pool vaporization model that we use in the study. So what is the time and what is the outcome of vaporization with the flammable cloud? But we only flash a vapor fraction is immediately available to be dispersed. So we have two models. We calculate separately, we include in the risk assessment, we add the probability, we add the wind, and blah, 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 and we have final risk. This is the challenge. This is the LNG. Next 50 years, it will not be hydrogen, green power. Fantastic, but LNG. The international project now are LNG. This is what happened. Then we can see on the papers, I don't trust. I have not understood. I have heard that hydrogen from ammonia. So the Fauser reactor, we started to produce ammonia. Now we produce ammonia and we recover hydrogen from ammonia. Fantastic. But maybe I'm not updating, maybe. Hydrogen is hydrogen. There are some international symposium, hydrogen. Sorry, but where can I buy hydrogen? From Amazon? Can I buy hydrogen? So I don't understand, but this is my limit, okay. So this is LNG. LPG is pressurized. LNG is not pressurized, is chilled. So we have essentially, as you can see, is methane, minus 161 degrees C, and you can this is now, in my opinion, the most important energy source in the world with the nuclear. The most important project that started after the pandemic in Middle East regarding LNG. LNG is already at atmospheric pressure, and a strong driving force exists, forcing it to boil without no flashing. Because no flashing, because there is no a gap between normal boiling and the atmospheric boiling. So it will be released and will vaporize because it is atmospheric pressure. It's not pressurized. And you can see how important it is to understand the physical chemistry when you are a process safety engineer. This is the dispersion scenario. Once again, section, turbulent jet, transitional laminar jet, momentum, blah, 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 blah. You can see a lot of, including the dense gas dominating regime. Sometimes you can have some heavy gas that are heavier than methane, but sometimes you can have also ammonia that, due to the temperature, behaves like a heavy gas because it is 17 molecular weight. But if you have 0 degree, the bulk density will be higher than the air. So we have a dense gas model. This is essentially what you expect to find when you have a release from a vessel. We have a first region. It's a little bit complicated to talk. Then you have a kind of transition. And then you have, in the end, the passive dispersion when the wind dominates and we move away the dispersion, the cloud. This is my article because I covered the first part after the release. And this is a turbulent flow, and I try to understand when we can be confident that we have left the flammable region between the low explosion limit and the upper explosion limit. This was published in the 2010, and is an article that has been validated by the FSA executive. I was a little bit surprised, but it happened. This is for laminar flow, so around, let's say, 5,000, because it is laminar. This is turbulent, depending on the Reynolds number. This is the model for the dispersion. As you can see, it is a Gaussian function. You can find that in reality, the molecular weight and the specific property of the vapor no longer play a role. It will be dispersed by the wind. Okay, this is, for example, an example. We have ethylene that is released, and we have a 15 millimeter hole. The gas speed is 300 meters per second, pressure, blah, blah, blah. And we have modeled essentially this release. Depending on the elevation, we have essentially the behavior of the concentration over the distance. Depending on, for example, ground floor, the ground, 20 meters and 10 meters. You can see how powerful is this model. It's very easy. You can find the sigma are tabulated, and you can calculate what happened at 5 kilometers, 10 kilometers, and so on. And you can find a question like this and diagram like this. It's very easy. Heavy gas, this is an equation, Brittle-McQuaid equation for heavy gas. So you have an heavy gas that can be on the ground, and so you can have some problems. You think that probably is swept away by the wind, but in reality it is heavy because the molecular weight or because of the temperature. You use Brittle-McQuaid. The pool evaporation, this is a way to say if I have a pool, I can calculate let's say the evaporation and the vapori mass flow rate according to a equation like this. Event tree analysis. Okay, this is, okay, what is the event tree analysis? In reality, Fricksboro, if they had been more lucky, they can have also a safe dispersal. If probably there wasn't just an ignition sort at the hydrogen plant, they possibly can have some dispersion with no problem. In reality, we have forced to have, we have a release. What happened? Release relevant, 0.3 against 0.7. Type of release, instantaneous, continuous. Direct ignition, we have some probability. This is event tree analysis. Analisi all'albero dei guasti. We assign a specific tabulated, validated probability, and we can understand what happens, what is the probability of oblivion, of flash fire, of explosion, of jet fire. So we have a profile of probability depending on the release, toxicity, everything. You can see this is event tree analysis. The source is TNO, that is the Netherlands organization, is the Dutch CNR. It's fantastic, it's one of the most important active institutions that provide a lot of information about process safety. The consequence assessment are essentially human vulnerability, fire explosion operational. Human vulnerability, we have another three: toxicity, lethality, occupational, fire, burns, explosion, lung damage. You can see every box is takes a lot of information. So you can have books and books for every box. You can imagine how important is the subject. This is a probability function. Probability function is a very important point. 30 seconds. We are almost finished the second, so please don't hate me too much. Here we have essentially probability function, maybe God thinks in terms of logarithmic function. Because you can see here from my books, the probability function for toxicity, from burns, from lung hemorrhage, from eardrum rupture, from glass breakage, from death from impact, injuries, for damage to buildings. Everything works according to a probability function. Probability function is this one. We have two constants, A and B, and we have an impact factor that is A. Okay, this is the table of probability. Normally, we calculate the probability that is essentially here. Then we cross-reference this to this and this, and we find the probability. What happens is this one. For example, this is the probability function for toxicity. You can see here we have A and B, ammonia, or hydrogen sulfide, or hydrogen cyanide. No? We have A and B. Then we have a concentration, C, and we have an explosive time, T. We have a probability function. There is an example. Hydrogen sulfide is relieved from the two falling units at the given frequency, A, okay, the first row. Calculate the risk index. So we have a population, we have the concentration, and we have the exposure time, 7 minutes. So we are exposed for 7 minutes to H2S at a concentration of 1,200 ppm. We go into we calculate, the probability function is 4.5. We assign 4.5 here, and we say 31% of that. This is a legal, important, probably the most accurate way to calculate one of the impact scenario, in reality is toxicity, for predicting what happens when you have a toxicity in place. And we have essentially other code, blah, blah, blah. Fire, I will be very, very quick. We have essentially jet fire. We can have jet fire that is a fire type resulting from combustion or pressurized release. We can have a pool fire. We have seen pool fire. We have a pool, and the pool is ignited here. And we can have essentially just the fresh fire. Fresh fire means that you have a flammable cloud with no pressure effect that burns. If you are inside, you die. If you are outside, you are safe, probably. In this case, not necessarily. If you are outside, you can die because of the thermal radiation. Fresh fire here is so fast that possibly it lasts, the duration is 1 to 2 seconds. So if you are inside, you die. If you are outside, probably you are safe. This is the models. This is essentially some correlation of a pressure explosion, you can see. And this is the last slide of the second one. If you have time, 10 minutes, we can show some software just to see if we have time, of course. I don't know. What is thermal runaway? Thermal runaway, in my opinion, is not properly covered in the safety studies. Sometimes, I remember in Saudi Arabia, sometimes during the hazard and operability studies, I claimed that some specific thermal runway had not been covered by properly. Neither nor by let's say the risk assessment, so were completely uncovered. It is a temperature pressure rise in a chemical reactor which can no longer be recovered by the system and escalates to an out of control situation resulting in loss of containment, fire, possibly explosion, unless the system is able to safely relieve the escalation thanks to the lessons of Benintendi. So if the system is not able, the control is not able to recover, you have a thermal runway. I don't know if you have studied the Seminole theory of explosion. You have two counterpart in terms. You have a Arrhenius curves, that is the reaction heat, producing heat. And you have a cooling water, for example. No? You have an heat exchanger. The point A is a stable point, because if there is if the Arrhenius curve is higher, in reality is trying to move up, the cooling water is able just to compensate, and you go back again to A. But if you reach the point B, is a tunnel runway, you cannot recover anymore. This is the Seminole theory of explosion. Thank you. I don't know if you want just to have 10 minutes. If we have time, otherwise we can stop. It's up to you. Yes? Yes, now it's something much more practical. Nicola, please don't try to escape.
Why am I saying?
Sorry?
Why am I saying?
Why? Because so no, I introduce, and then you can we connect the laptop?
Yes.
So we can show what will happen when we use it. So sorry, there is a third one for 10 slides, just it's illustrative, and then Nicola can provide you with a specific, you say, as of study, so we can show you what happens here in a true study. So the third module?
Yes.
This is just an introduction, eh? No, I don't want to bore you anymore. Okay, thank you. Okay, risk assessment, you can see here, individual risk for thermal, individual risk for overpressure. This is a real case, real study, and the toxic LSIR curves. We normally calculate this, and then we sum of them, and we obtain the overall LSIR. This is a quantitative risk assessment study, real. Then we have essentially the hazard and operational status. When you go into wherever you will go after your degree, you will attend some of these studies. So be prepared. Hazard, seal, low power. What is hazard? This is essentially a node. These are two reactors, ammonia reactors. We have some node. Node is a part of the plant that we have essentially just, separate from the remaining equipment. And normally we use the node distribution because we consider that the process temperature and pressure are the same. So the node number 8. This is a hazard. Hazard means hazard identification. As you can see, the number 8, we have jet fire, flash fire, explosion, toxicity. The typical guide or loss of containment. We identify the causes. We identify the consequences. We identify the mitigation and any additional action to reduce the hazard. Normally this starts at the beginning of the study, in the preconceptual phase of the design, in the engineering activity. The hazard, you can see here, for example, we have, this is a separator, Nico, separatore. This is a separator, this is a fuel gas coming from a fuel gas line, methane. This is a liquid gas separator, node number 1. And this is a hazard. The hazard, I think, maybe you have been introduced, I don't know, probably you have talked about hazard. No. Anyway, this is a hazard means hazard and operability study. This is one of the more boring, long, stressing, yes, for sure, especially from remote. 42 days, 8 hours a day, connected with India, UK, Netherlands, you can imagine. We have some deviation. This is a deviational approach. There is something that is not exactly complying with the process parameters. No, less, more, misdirected, reverse. Flow, temperature, pressure, something is departing. So this is a brainstorming method. Normally this is carried out by 10 people, 15 people, 20 people. Every discipline, process, structural, instrumental, maintenance, the manager around the table, you can imagine. And we have a cause. We identify, for example, undue closure of a valve number this. This is a consequence. This is a category. A means asset, S means safety, E means environment. We have a safeguard. and we have essentially some additional action if the risk is not acceptable. Guide word by guide word, you can imagine, you have the identification of all the valves, all the pressure transmitter, everything. You can imagine with the P&ID. In the end, if you are relying, okay, you can see here, for example, more pressure, low pressure, high differential pressure, more temperature. This is a real case study. Sometimes you require some specific protective action from a loop. So you can say in blue, LOPA required, yes. So it means that you are relying, no? You are, ti stai affidando, you are relying on safeguard. There is a pressure safety valve. There is a shutdown valve. There is a pressure save valve. So is layer of protection required? Yes. It means that you have to consider what is the reliability and the fault rate of that instrument. I see on your eyes that you are maybe planning to change your study course. It's too late. You cannot go to become a lawyer. I don't know, gym, physical training, or becoming a top model, maybe you can. But this is what happens in your future. Regardless of your discipline, you say, okay, I don't like it. I don't like it because, but sooner or later you will be involved in this. This is what expect you. I don't know if you were working on polymers. I don't know. So you are against polymer. I know nothing about polymer. But polymers now is from Thailand, so you can have a distribution of the market. This is what happened in every project. This is what happened in every project. What means? You can see this is the onion arrangement. Onion, cipolla. You have the process hazard, and you must be safe. In between, you have the process design and basic control, Professor Mitchell. Now you have the instrument. Then you have a critical alarm, you have the alarm. Then you can have physical protection, plant emergency response, community emergency response, and in the end, God. Madonna, God, San Gennaro, depending on your religion, no? So you have to pray. But in between, you have automatic ISS. Automatic ISS is exactly, you say IPL, yes. Nicola, it's up to you, please.
10 minutes break or we go.
Exactly.
I need some time to
Okay,
to prepare.
it's another 10 minutes, then you are completely, you can change your...
Thank you very much. It is a non-stop. Sì, si vediamo.
Lui poi fa questi 10 minuti, ma fa vedere un po'. E poi va bene.
So registration will be stopped now. We will continue with an application that is impossible to transmit. Okay, thank you very much to all the people that is related to it. And I will stop now.